Hello, class. In our daily life, electronic products can be seen everywhere. They all require power sources, providing significant convenience to both production and daily life. However, during the use of electricity, occasional electrical accidents may occur. In this chapter, we will explore various knowledge about the safe use of electricity to ensure our peace of mind when using electrical devices. First, let's understand some concepts related to the safe use of electricity. Electricity. On one hand, electricity can benefit humanity, bringing convenience to production and daily life. On the other hand, it can pose a threat to humans and in severe cases lead to electric shock injuries or fatalities. In the process of using electricity, it is crucial to prioritize safety and adopt a preventive mindset. Safe electrical use encompasses both personal and equipment safety. Personal safety refers to preventing electric shock and other electrical hazards in both industrial and daily life settings. Electric shock occurs when a person accidentally comes into contact with the live parts of electrical equipment or circuits, resulting in personal injury. Depending on the severity, this can be characterized into electric shock and electrical injury. Electric shock refers to the passage of current through the human body, causing pain, numbness, muscle spasms, and in severe cases, intensive convulsions, cardiac fibrillation, or even fatal injuries leading to death. The degree of harm from electric shock is related to factors such as the magnitude of the current passing through the body and the duration of exposure. The vast majority of fatalities due to electric shock as a result of the shock itself. Electric injury refers to electric shock that occurs when there is poor contact between the human body and the charged body, resulting in arc burns or electric branding. It can also occur due to the melting of the contact part by electric current and the disposition of evaporated metal particles and evaporated metal particles, etc., on the skin, causing skin metallization. Electric injuries have the potential to leave lasting scars on the human body. In severe cases, electric injury can be fatal, leading to loss of life. It is not uncommon for electric shock and electric injury to occur simultaneously, especially in high-voltage electric shock accidents. Generally, human body resistance ranges between 1,500 to 2,000 ohm. Taking power frequency current as an example, when a current of about 1 milliampere passes through the human body, it will cause uncomfortable feelings such as tingling. A current of 10 to 30 milliampere flowing through the human body can cause paralysis, pain, elevation of blood pressure, dyspnea, and other symptoms, but usually not life-threatening. However, when the current exceeds 50 milliampere and lasts for more than 1 second, it will cause ventricular fibrillation, which is life-threatening. A current of more than 100 milliamps is sufficient to cause loss of life. The degree of harm caused by current to the human body is related to both the magnitude and duration of the current flow. The larger the current, the more pronounced the sensation, and the greater the degree of harm. Safe voltage refers to voltage that does not directly cause death or disability. Under normal environmental conditions, safe voltage allows for continuous contact. The safe extra low voltage is typically 36 V. Safe voltage should meet the following 3 conditions. The nominal voltage does not exceed 50 V AC. DC voltage is limited to 120 V, and it is powered by a safety isolation transformer. The safe voltage circuit is isolated from the power supply circuit and earth. According to the characteristics of the production and workplace, the corresponding grade of safe voltage should be adopted. This is the fundamental measure to prevent electrical accidents resulting in electric shock injuries or fatalities. The national standard safe voltage stipulates the grades of safe voltage rating in China, which are 42V, 36V, 24V, 12V, and 6V. The selection of safe voltage depends on factors such as the workplace, operator conditions, usage mode, power supply mode, and line conditions. For example, in particularly dangerous environment where handheld power tools are used, 42V extra low voltage should be adopted. In an environment with electric shock hazard, handheld lightning and local lightning should use 36V or 24 extra low voltage. In a metal container, particularly dangerous environments such as particularly humid places, handheld lightning should use 12V extra low voltage. For underwater operations and other places, 6V extra low voltage should be adopted. According to the way the human body touches the charged body and the path of current flow through the human body, electric shock can be divided into low voltage electric shock and high voltage electric shock. Among them, low voltage electric shock can be divided into single-phase electric shock and biphasic electric shock. High voltage electric shock can be divided into high voltage arc electric shock and step voltage electric shock. Single-phase electric shock refers to the phenomenon where the human body directly touches the live part of an electrical device, allowing the electric current to pass through the body and flowing into the ground. This electric shock phenomenon is called single-phase electric shock. Electric shock caused by high voltage charged bodies, although the human body is not in direct contact. However, due to exceeding the safe distance, can still result in high voltage discharging to the human body, causing single-phase grounding and subsequently leading to an electric shock. This type of electric shock is also classified as single-line electric shock. Biphasic electric shock occurs when the human body comes into simultaneous contact with live equipment or two phase conductors in a line, or in a high-pressure system. As the human body approaches two-phase charged bodies with different phases, an arc discharge takes place. The current flows from one phase conductor and passes through the human body to another phase conductor, forming a closed circuit. This type of electric shock is known as double-line electric shock. When double-line electric shock occurs, the voltage acting on the human body is equal to line voltage. This kind of electric shock is the most dangerous. High voltage arc electric shock. High voltage arc electric shock refers to the situation where people are near high voltage power lines and experience electric shock due to arc discharge. Arc discharge occurs when there is a high voltage present, even without direct contact. During the approach to high-tension transmission lines, people may witness a brief flash of light and can be knocked down, resulting in electric shock or even death. For instance, when the resultant force switch sends power, an arc may erupt and potentially burn the operator's arms, face, and eyes. Step voltage electric shock occurs when there is a grounding fault in electric equipment, and grounding current passes through the grounding body, scattering to the earth, forming a potential distribution on the ground. If a person walks around the grounding short circuit point, there is a potential difference between his feet, resulting in step voltage. Electric shock of human body caused by step voltage is called step voltage electric shock. The magnitude of step voltage is influenced by factors like the size of the grounding current, footwear, and ground features. The span between 2 feet, the orientation of 2 feet, and the distance from the grounding point. When the threat of step voltage is detected, it is important to quickly put your feet together or use one leg to jump out of the danger zone. Prolonged exposure to electric shock can lead to electrocution. To effectively prevent electric shock accidents, measures such as insulation, screen protection, safe spacing, protective grounding or zero connection, and leakage protection should be employed. Insulation. Insulation is the use of insulating materials to enclose the charged body. The insulation only fails when it is damaged. The volume resistivity of electrical insulating materials is generally above 10 to the power of 7 ohm meter. For newly installed and overhauled low voltage lines and equipment, the insulation resistance should not be less than 0.5 ohm. And for running lines and equipment, it should not be less than 1000 ohm per volt of working electricity, or 500 ohm per volt working voltage, when operating in a humid environment. In a control circuit, the insulation resistance should generally not be less than 1 ohm, or can be reduced to 0.5 ohm in a humid environment. For high voltage lines and equipment, such as 35 kV, the insulation resistance should not be lower than 1000 to 2500 ohm. The insulation resistance of cables in operation according to its rated voltage should be set between 300 to 1500 ohm. Before putting the power transformer into operation, its insulation resistance should not be less than 70% of the factory value. Insulation, due to breakdown, damage, and aging, will lose or reduce its insulating properties. In the presence of factors such as a strong electric field, the insulator can completely lose its insulating properties, which is known as breakdown. After gas breakdown, it can restore the insulation performance by itself. After liquid breakdown, it can basically recover or restore the insulation performance to a certain extent. However, after solid breakdown, the insulation performance cannot be restored. Damage refers to insulation that is damaged due to corrosiveness, gas, vapor, dust, and mechanical factors, which can reduce or even lose insulation performance. Aging refers to the gradual deterioration of electrical and mechanical properties of insulation. Under the action of electric, heat, and other factors, if insulating materials of charged bodies are damaged by breakdown or aging, there will be current leakage. For equipment or appliances with high safety requirements, such as insulating gloves and insulating boots, insulating pads, etc., as well as high voltage facilities, such as circuit breakers, transformers, power cables, etc., and household appliances and power tools. Leakage current tests should be carried out regularly to discover in time internal defects like hard injuries, brittle cracks, and meanwhile, dielectric loss test should also be regularly carried out on insulating materials to ensure their insulation performance by taking strong measures. Screen protection and spacing. Screen protection is achieved by using barrier materials to prevent contact with charged bodies. It can not only prevent electric shock, but also protects against accidents such as arc burn and arc short circuit. Materials used for screen protection device should have sufficient mechanical strength and good fire resistance. They can be made into plate-like, net-like, or grid-like shapes according to site requirements. Spacing refers to the distance between charged bodies and the reach of people and equipment. It is a safety measure to keep the charged body away from the ground, other equipment, and facilities with necessary safe distance maintained. Proper spacing also promotes maintenance safety and prevents electrical fires, short circuits, and other accidents. The spacing size should be determined based on voltage level, device type, environmental conditions and installation method, etc. In order to prevent the human body from approaching the charged body, sufficient maintenance spacing must be reserved when installing the charged body. In low-pressure operation, the distance between the human body and its tools and the charged body should not be less than 0.1 meter. In high-pressure, unobstructed operation, the minimum distance between the human body and its tools and the charged body should not be less than 0.7 to 1 meter. Protective grounding involves holding it equipotential with the earth so that even if the internal insulation of the electrical appliance is damaged, its leakage current can flow into the earth through the grounding system, and the metal shell of the appliance will have no voltage. Therefore, there will be no danger if the human body comes into contact with it. However, this method is only applicable to three-phase, three-wire power supply systems that have no neutral line and whose neutral point is not directly grounded. Protective connect to neutral is suitable for three-phase, four-wire power supply systems with a neutral line directly grounded. It involves connecting the uncharged metal shell of household appliances to the neutral line of the power supply line. Once the insulation of the live conductor is damaged, its phase line, metal shell, zero line will constitute a short circuit, generating a large short circuit current. This can blow the fuse on the power supply side or trigger the automatic switch for overcurrent tripling, cutting off the power supply and eliminating the risk of electric shock. Currently, China's domestic power supply mostly consists of three-phase, four-wire systems with neutral points that are directly grounded. Therefore, this method is widely used. Protective cutoff is intended to prevent electrical short circuits, which can cause the fuse on the power supply side to blow or the automatic switch to trip, thereby cutting off the power supply. This is based on the occurrence of high currents. Besides, both domestically and internationally, the protection method of protective cutoff has been implemented based on household appliances that do not have a charged metal shell. When the voltage becomes higher than the safety voltage, the power supply is immediately cut off. This method is a very effective protective cutoff method designed to protect personal safety and prevent electric shock accidents. Voltage-type electric shock protection is a method that relies on household appliances with an uncharged metal shell. The voltage to ground is used as the action signal as long as the metal shell experiences a decrease in insulation of a live conductor, resulting in leakage, and the numerical value reaches the safe voltage for human contact. The protective switch operates immediately. It disconnects the automatic switch on the power supply side, cutting off the power supply. Current-type electric shock protection is based on household appliances with an uncharged metal shell that generates a leakage current to the ground as an action signal. Under normal conditions, fire line and working zero line carry currents of equal magnitude but opposite directions. The protection switch remains inactive without a signal. However, if the phase line experiences a decrease in insulation and leakage occurs, the leakage current passes through the metal shell of household appliances and the human body, and it reaches a numerical value close to the limit value of human contact safety current. As a result, the protection switch activates and the switch trips, cutting off the power supply. This lesson has ended. Now let's consider the different forms of electric shock and determine which one is the most dangerous. Additionally, what are the ways to prevent electric shock? As for more knowledge, see you next time.